I'll address your question.
All right.
Yeah. All right. I wanted to just revisit problem 16.1 for just a moment. Last time I had written this equation where delta G under standard conditions is going to be equal to minus n times F times delta E. Okay. And I think I may have forgotten to put this minus sign here. So I want to let you guys know that's going to be a negative 164 kilojoules per mole, as long as we go from the acceptor, the final acceptor to the final donor. Okay, so that's what we should have there. So and actually, I think the problem is really about the amount of energy per mole of electrons that get through the system. Now there was an interesting question that just came up from one of your classmates, and that is, why do we choose 1 for that value? And let's go ahead and read the problem really carefully so we can come up with that. So this is going to be problem 16.1. Okay. So according to figure 1612b, upon excitation, the P700 reaction center is raised in potential from plus 0.4 to minus 1.3 volts. To what value of delta G under standard conditions does this correspond? How does it compare with the energy in an Einstein of 700 nanometers of photons, of 700 nanometer photons? So why do we choose 1? We're choosing 1 as if it's going to be 1 mole of electrons. And I think an Einstein is going to be defined as, let's go back here. What is an Einstein? An Einstein, this is on page 677. An Einstein is a mole of photons. So a mole of photons is going to excite a mole of electrons. So there's a 1-to-1 correspondence. That's the same as saying 1 photon is going to excite 1 electron. So we're trying to figure out what the energy is in a mole of photons and what the energy is in terms of moving or exciting 1 mole of electrons. Does that make sense? Okay, so that's why we use the 1 there for that value. Okay. Next, let's go ahead and do 16.2. Okay, so 16.2. In cyclic photophosphorylation, it is estimated that 2 electrons must be passed through the cycle to pump enough protons to generate 1 ATP. Assuming the delta G value for hydrolysis of ATP under conditions existing in the chloroplast is about minus 50 kilojoules per mole, what is the corresponding percent efficiency of cyclic photophosphorylation using light of 700 nanometers? Okay, let's point out a couple of things here. We're talking about 2 electrons moving, number 1. Number 2, this delta G is different than this delta G. So this delta G is the actual delta G, not under standard conditions, but the actual delta G. That's why they have a value which is going to be minus 50 kilojoules per mole. If we had said delta G under standard conditions for hydrolysis of ATP, do you guys remember what would be the value for kilojoules per mole? Negative 30.5, right? So that's why this is a little bit different. And if you think really carefully about the equation, what's happening is that the products are lower in concentration than the reactants. If you work out the equation there. Okay, so we're trying to figure out efficiency of the cyclic photophosphorylation system. Okay, so we have the end. So we'll just go ahead and write 16.2. We have some information. We have ATP plus water is going to give us ADP plus inorganic phosphate, and they give us the delta G value is going to be minus 50 kilojoules per mole. Okay. And the question is, what is the percent efficiency of photophosphorylation and we're supposed to be using light with light that has 700 nanometer wavelength. Okay. So we already figured out that from problem, I'm going to say from problem 16.1, that 1 mole of photons is going to give us 170 kilojoules of energy. Already figured that out. Okay. Therefore, we need 2 moles of photons to excite two moles of electrons. Thus, 2 times 170 kilojoules is going to be equal to 340 kilojoules. Okay. So the percent efficiency is going to be equal to the absolute value of the chemical energy in ATP divided by the energy in the photons multiplied by 100 . So the percent efficiency is going to be equal to the absolute value of minus 50 kilojoules divided by 340 kilojoules multiplied by 100 and that's going to give us 14.7%. Okay, so that's the efficiency of converting the light energy into ATP. Actually, it's a bit less than that, because those are the productive photons. So in other words, many of the photons will shine light onto the leaves, but they do not make productive transfer of electrons from one chlorophyll to another. They get excited, then they come back down into the same molecule. Only on relatively few occasions will the electrons get excited and go to a higher orbital in the chlorophyll and also get transferred to the next chlorophyll. Then that's where the electron transport actually occurs. Okay, what about number 3? We did something like this in class, but this is going to be in a I guess, problem setting. Assume a pH gradient of 4 units across the thylakoid membrane, with the lumen more acidic than the stroma, which is what we expect for a plant, right? What is the longest wavelength of light that could provide enough energy per photon to pump 1 proton against this gradient, assuming a 20% efficiency in photosynthesis, and they give you a temperature of 25 degrees Celsius. So the longest wavelength, basically the lowest amount of energy, the longest wavelength, lowest amount of energy. Okay, so let's go ahead and set up this problem. So they give us that the delta pH value is going to be equal to 4.0. And I'm just going to just jot down some things from the problem. They want the longest wavelength of light. And it's going to have to provide enough energy to pump 1 proton against the gradient. Okay. And we're also given that the temperature equals 25 degrees Celsius, which is the same thing as 298 Kelvin. So I just did that conversion there. So the way I approach this is I broke this down into 3 parts. Determine the frequency I'm sorry, not the frequency. Can't even read my own writing. Okay. I determined the free energy. In other words, the delta G per proton to move a proton across the gradient. B, use the delta, the free energy, to calculate the lambda using the equation energy equals Planck's constant times the speed of light divided by lambda. Okay. And then C, don't forget to include 20% efficiency. So that sort of maps out what I want to do. Okay. So we know that the delta G, so let's go ahead and just draw our membrane here. I like to draw these little figures to help me out. So we have a large amount of protons on the inside of the thylakoid, small amount of protons on the outside. This is called the lumen. Okay. And I know that the general equation for delta G for particles across a membrane is this, where you have delta G is going to be equal to the electrical energy plus the chemical energy. So in general, that's it, okay? However, we know from experiments that this electrical component is 0 volts, okay? So we don't have to worry about that, okay? So now we go ahead and write down our formal equation, delta G. And I'm gonna, because this is gonna be against the gradient, I'm gonna go from out to in. Okay, so in other words, I'm trying to pump a proton from the stroma into the lumen. Okay, and so that's going to be equal to RT natural log C in over C out. Okay. Now, if I had said in to out, if I had drawn my arrows going from in to out, then these two get reversed. Okay, so that's the way to think about this. Now, before we even start putting in numbers in here, let's think logically what's going to happen. We're going from out to in, right? So do you expect delta G to be positive, negative, or 0? Beautiful, positive, exactly right. It's going to take energy to move that proton against that gradient, okay? So it's going to be positive. Okay, if you think it's going to be, okay, so you've already logically figured out that's got to be positive. What do you think this value has to be? Does that value have to be greater than 1, equal to 1, or less than 1? Beautiful, it's got to be greater to 1. If it's going to be greater to 1, then you know that this is going to be a positive term, okay? And it makes sense that the concentration on the inside is going to be higher than the concentration on the outside, right? Makes total sense. So now what we're going to do is we're going to use this value that the delta pH is 4.0, and we know the concentration on the inside has to be higher than the concentration on the outside. I already talked about this in lecture, okay? And if you just look at my, I think it was maybe my previous lecture or the lecture before that, we're just going to assume, all we have to do is make sure we assume the correct difference in pH. We're going to assume that the inside, protons on the inside, let me see, how do we do that? Okay, we're going to say pH equals minus log. I'm going to say of protons, okay, and we're going to say this pH, if it's on the inside, is going to be equal to, let's say, 4, okay, and we're going to say the pH on the outside is going to equal minus log of protons on the outside is going to be equal to 7. Okay, that's a pH difference of 3, and I also have it set up correctly so that the pH on the outside is higher than the pH on the inside by, wait, did I do that right? Oh, darn it, no, my math is wrong. Okay, hold on here. Let's reverse this. This is wrong. That should be 8.0. Why was I wrong when I said 7?
The delta pH is 4.
That's right. So, got to think right. Okay, so now I have the delta pH is 4, right? Exactly right. So the difference between 8 and 4 is 4. So now I've accomplished what I wanted to for this this problem. Okay. Now it's simple. All I have to do is calculate the amount of protons on the inside. So protons on the inside is going to be equal to 10 to the minus 4 molar. You guys can do the calculation, but it's very simple. And then protons on the outside is going to be equal to 10 to the minus 8th. So we just put those values in there, and now we have the delta G value. So delta G out to in is going to be equal to 0.008315 times 298 times the natural log of 10 to the minus 4 divided by 10 to the minus 8. Okay. And if we calculate that, I get a value of 22.8 kilojoules per mole. I noticed in my notes here that I actually used pH 7 and pH 3, which was a difference of 4. It doesn't matter, okay? As long as you have this difference in concentration of 4 pH units, you're fine. Okay, so that's a positive number, which is good, and so that's how much energy it takes to pump a mole of protons across that gradient, and it's endergonic because you're going against the concentration gradient. Beautiful, beautiful. Now I'm going to just convert this to the amount of energy per proton, not molar protons, but per proton. In order to do that, what essential number do I need in order to convert this to a per proton basis rather than per mole of protons? Avogadro's number, exactly. So on a per proton basis, delta G out to N is going to be equal to 22.8 kilojoules per mole times 1 mole equals 6.02 times 10 to the 23rd protons, right? Oh, did I do that calculation? Hold on here. Okay, that's what it is. I'm not sure why I don't have that here. Okay, so that should be the you guys can figure that out. Okay, next I need to figure out what is the energy associated with this. I'm sorry. What is the lambda value associated with this? Okay. So I'm on to part B of my work here. So I said lambda equals Planck's constant times the speed of light divided by energy. And I have energy, that's this value right here, okay? And so all I have to do is now figure out, oh, you know what I did? Okay, actually I don't have to actually go through this process. Okay, it's fine that I did. Can you guys do this calculation for me? What is that?
3.79 times 10 to the negative 23.
3.79 times 10 to the minus
23, yeah.
23 kilojoules. Thank you. Okay, lambda is going to be equal to this energy. Okay, so all I have to do now is just plug in all these values in for this. So it's going to be, lambda is going to be equal to 6.626 times 10 to the minus 34 joules times seconds times 3 times 10 to the 8th meters per second. Okay. I'm running out of room here. That gets multiplied by 1 divided by 3.79 times 10 to the minus 23rd kilojoules. I got to put in some conversion factors here. Let's see here. 1 kilojoule is the same thing as 1,000 joules. Okay. And 1 times 10 to the 9th nanometers is the same as 1 meter. And what is the number of nanometers that we get from that? Hope you guys get what I got. Five thousand 244.85 nanometers. We'll just say 5.2 times 10 to the third nanometers, right? Okay. So that is the wavelength of light, but I'm missing one thing. I didn't talk about efficiency, right? So in order to think about efficiency, if the efficiency is only 20%, I need to increase my energy accordingly. In order to increase the energy, I need to multiply 20% times this wavelength of light, and that will shorten the wavelength of light appropriately to account for the inefficiency. C, efficiency equals 20%. Therefore, wavelength of light is going to be equal to 0.2 times 5.2 times 10 to the third nanometers. That gives me 1.04 times 10 to the third nanometers, which is approximately 1,000 nanometers. Okay, 1,000 nanometers of light. That's the wavelength. Okay, we are done with chapter 16. We're ready to talk about fats. And just to orient you, we'll look at this overview of this metabolism. Okay. So earlier we had talked about glycolysis. So we talked about this central pathway going all the way down to the bottom here where you have oxidative phosphorylation. We talked about gluconeogenesis. We made a detour and talked about photosynthesis and how photosynthesis supplies carbohydrates for storage, and so we talked about this. Now we're going to be talking about this wing, where we have lipids that get degraded into fatty acids and glycerol, and those fatty acids are then going to be broken down into acetyl-CoA, and that acetyl-CoA will be able to enter into the citric acid cycle. I'm not sure why this isn't yellow, but anyway, it does. It enters the citric acid cycle, and also the fatty acids will directly, in this process, make NADH and FADH2. That process is known as beta oxidation, so going from fatty acids to acetyl-CoA. The glycerol, does anyone remember how many carbons glycerol has? Has 3 carbons. And you guys remember how many carbons glyceraldehyde 3-phosphate has? It also has 3. So glycerol can get converted into glyceraldehyde 3-phosphate, and then that can also be used for either going, it can be used for going eventually to the citric acid cycle as well as oxidative phosphorylation. So the glycerol gets converted into glyceraldehyde 3-phosphate. So we'll talk about this. But before we do this, I'd like to sort of open this up to a more general discussion about the weight difficulty in the United States. And you guys have probably heard this in the popular press. I know Michelle Obama has been big on this, so let's go ahead and talk a little bit about this. So we put this into context, how important it is to know about this metabolism and how we can sort of fight an epidemic which is coming on in the United States. So it turns out that, so this is obesity. So it turns out that 1/3 of US population is overweight. 1/3 of US population is what we call obese. So that means 2/3 of the population is really over what's considered the normal weight of individuals. Turns out that we'll talk about that in a sec, what that means normal. 15% of children between 6 and 19 are overweight or obese. Okay. And 25% of dogs and cats are overweight in America. Okay. And a fairly recent poll said that 58 polled Americans and said 58% of Americans would like to lose weight. Okay. Of course, we know that there's a lot of risks associated with obesity. You know, there's heart disease, there's stroke, there's diabetes. And then it seems that now poor diet and physical inactivity is overtaking tobacco use as the leading cause of preventable death. Oh, it helps if I spell death correctly. Hold on. Death. And this is an epidemic that has started fairly recently. So I'm going to write down a table here. Percent of population obese that is obese in the US, ages 20 and up. It's quite startling, actually. So from 1976 to 1980, the average was 15.1%. From 1988 to 1994, it was 22.9%. From 1999 to 2000, the percentage was 30.5%, and from 2009 2010, it shot up to 35.7%. I think we've been holding at 35.7% or around 36% since then. So it hasn't changed so much since then. Diabetes, the incidence of diabetes. In 1980, the percentage of people in the United States that had diabetes was 2.8%. In 2000, it's 4.2%. In 2011, 8.3%. So obviously, the statistics are telling us that there's something happening here. So I'd like to open this up. What do you guys think is happening? Yeah.
The change in how the food industry processes food.
Okay. So you think that the food industry has been processing food differently since 2000? Since 2000?
Well, like from like the late like in the 50s.
Yeah.
It was different how food was made compared to now.
Okay. Okay. But I mean, this is more than a doubling during the modern era since 1976,
Mm-hmm.
and we've had food processing for a while. But I agree that food processing has something to do with it. Yeah.
In roughly around the 1990s, when fats were demonized as the cause of weight gain at the time,
Uh-huh.
they started taking the fat out of things and instead adding sugars in order
Okay.
to make them palatable.
Okay. Okay. So there's been this whole effort to make things low fat or non-fat, and in order to compensate for that, in order to make food still taste good, you've got to put carbohydrates or sugars into them, right? Very good. Very good. I hadn't thought about that. That's interesting. Yeah.
There's like a lack of exercise and people and their metabolism starts going down and they can't exert that much, or they don't, the energy in their body isn't used as much as when they were younger.
I think that's totally true. I mean, the amount of time that people sit and do work as a population has increased tremendously since even the 1980s, right? Because of the type of jobs that we do. Yeah. There was somebody else. Does anybody else have any contributions to this? Okay.
They've also found a correlation between our higher sugar intake and our microbiome, which is changing how we metabolize food. Not just what we're eating, but how it's being processed inside us.
So microbiome, what is the microbiome?
The gut microbiome, all the microbes that live in your intestinal tract.
So they've changed, and maybe somehow they are maybe not metabolizing as much of the food as before. Interesting.
Or more efficiently. There's different microbes metabolize what we intake at different efficiency levels. So the microbes that they have found associated with obesity also have a tendency to metabolize their energy more efficiently, therefore extracting more energy from the foods that we eat.
So let me get this straight. The microbiome, I'm not very familiar with this, to be honest, but the microbiome, you thinking that they extract energy more efficiently?
Right. So they have found, or what I've been reading is that they found that our population gets roughly up to 10% of our energy intake from byproducts that our microbiome has processed,
Oh.
and that
So if they're more efficient, then we start taking in more of their stuff.
exactly.
How interesting.
So
I didn't know
if you
that.
eat something, it might be a certain amount of calories, but you're not going to get all of those. Not all of it is going to be processed into energy, but with certain microbiomes, more of that is processed into energy than it would have been otherwise.
Okay. Okay. Cool. Cool. What else? Any other reasons why this epidemic is here besides physical activity, and change of diet, and which is causing microbiome changes? Anything else? What about this concept of the lack of good foods in certain neighborhoods, right? I think they call these food deserts. Have you heard of this? Where you can go to some place in Los Angeles and you can go for miles and you don't find a regular grocery store, but you'll find McDonald's and Burger King and all these other places, but not a regular grocery store. And what are those people going to live off of within walking distance? Yeah.
I'm going on to like what you said too, like
So, like for example, what?
Like organic foods tend to be a bit more pricey
Yes,
than
yes.
the cheap fast food.
Yes, yes, yes. Organic foods are definitely more pricier. Yeah, yeah. Yeah.
Healthy foods are also more time consuming. Like to cook for yourself, to cook vegetables, to prepare vegetables takes a lot more time.
So that's a really good point. With most people in the household working now, there's not enough time to really prepare a meal from raw ingredients anymore, right? It's much easier just to stop by at a certain place and pick up processed foods and feed that to the family. And the goal of processed foods mostly is to have you come back and get more processed foods. So you got to make it taste good, right? So I think I think changes in lifestyle is part of this as well.
I guess you could also include maybe a lack of self-control.
So lack of self-control, yeah, me.
That's the microbiome actually. There's a lot of evidence that they're telling us what they want to eat.
Really?
But
I wish I could change my microbiome.
Yeah.
Okay. So this lack of self-control is interesting because you probably we're all aware that the wide availability of food in our civilization for much of the history of modern humans being around on Earth wasn't available, right? And so it's only within the last maybe 100, 200 years that you could actually have 2 or 3 meals a day, maybe even 100, maybe just 100 years, right? Most people lived off of maybe having something once a day, and you're talking 300, 400 years ago, you'd be lucky to get something like once every 3 or 4 days, right? You have to hunt down your food or gather your food and eat a lot of it at that particular time. There was no refrigeration to keep it around, and so we're mentally stimulated to eat as much as we can and probably as quickly as we can in order to store it around for weeks at a time, so that when the next food becomes available, we can get that. So we are not, evolutionarily, we are not geared towards this sort of 3 meals a day, balanced and everything. It's just not in our DNA to do this. Our DNA tells us eat a lot and then starve for like maybe 3 or 4 weeks, and then eat a lot and then starve for 3 or 4 weeks. So we can actually go for a long period of time. I don't suggest doing this, but you can actually go for a long period of time without eating and just surviving off of water. So it's pretty amazing. Of course, our bodies will change, but it is possible to do that. So where does all these values come from? You probably know this, and this is very debatable. This whole concept called BMI, which stands for. Everyone knows that. Okay, body mass index. And here is one scale, and I know, as I said, this is debatable, but I'll just put it down here. What is the body mass index? Shouldn't it be different for different folks, for different body types? I agree with all of that, but let's just, for the sake of argument, so that's just status. So we have, when you're below 18.5, you're considered underweight. When you're between 18.5 to 24.9, you're considered normal. When you're between 25.0 to 29.9, you're considered overweight. When you are between 30.0 to 39.9, you're considered obese. And when you're above 40, you're considered what? Morbidly obese. And And one way to calculate BMI is BMI is going to be equal to weight in pounds divided by height in inches squared times 703. So just take me, for example, sadly, okay, and if I exercise a lot and don't drink any water for like a whole day, I can get down to 190, okay, and my height is 5 foot 8.5, but I'm going to round that up to 5 foot 9, so that's going to be 69 inches squared, okay, and if I multiply that by 703, I come out to 28.1. That's sad. Okay. So, and I'm doing everything in my power to, not creep up to the obese level, but it's hard. You exercise, but you gotta sit down at the computer, 12 hours a day or whatever I do, and I try to eat in moderation, but still, it's really difficult. So next time we get together on Monday, we will talk about fatty acids, digestion. We'll talk about what happens when you eat a juicy $6 burger from Carl's Jr. and how the fat gets digested and transported and metabolized. Also, I want to let you guys know that next Friday is the Friday before Memorial Day, isn't it? And I will be going to Northern California that day, early in the morning. So you guys will not have a lecture. I'll try to put something together, probably something short for video for Moodle for that day. So there'll be no class a week from today. All right.